Greetings to another discussion of the homework number 7. We'll be looking at two questions from the AP Statistics exam in 2015, number 3 and 4. Number 3 is a probability question, always good to review probability. Number 4 is an inference question, a 4-step process. So we have a shopping mall has 3 automated teller machines known as ATMs. Because the machines receive heavy use, they sometimes stop working and need to be repaired. That's what my brother-in-law does for a living. He repairs ATM machines. Let the random variable x represent the number of ATMs that are working when the mall opens on a randomly selected day. The table shows the probability distribution of x. Number of ATMs working, 0, 1, 2, 3. Probability given right there. What is the probability at least one ATM is working? At least one would be 1 or more, 1, 2, or 3. So that probability is simply the sum of these probabilities. Now, if you wrote just this answer, this would be at best a partial because there's no supporting work. Now, if you wrote 1 minus the complement, 1 minus the 0 case equals that, then that would be sufficient. But otherwise, you would need to write what you're actually summing up to get full credit, to get an E on this part. So work and the answer. Letter B, what is the expected value of the number of ATMs that are working when the mall opens? Expected value is the same as asking what's the mean or what's the average. So looking at the values, it seems like the average is going to be somewhere between 0 and 3. If you get an answer bigger than 3, that wouldn't make any sense. How can like 3.5 ATMs be working on average if there's only maximum of 3? So to find expected value, there is a formula for expected value on the formula sheet. It looks something like this. The expected value of x equals the outcome of the random variable times the probability of that outcome, and then you add up all of those. Notice here there's no division by like 3 or divide by 4 or anything like that. It's tempting to do, but the division is dealt with within the probability. The probability is a quotient, basically a ratio. So the answer we would get, we'd have 0 times 0.13 plus 1 times 0.21. This is a weighted average, basically, plus 2 times 0.4 plus 3 times 0.24. That would be the supporting work that you would need to show, and the answer we would get is, looks like 1.73 ATMs. So on average, we expect 1.73 ATMs to be working when the mall opens. That is the expected value. That is also worth an E. So on this question, pretty fast so far. Might not be spending our average of 12 minutes per FRQ on a question like this. But hopefully the first 2 parts, you're able to get 2 points on that. The next 2 parts are also worth 2 points. Part C says, what's the probability that all 3 are working when the mall opens, given that at least one ATM is working? When you see a term like given that something else has occurred, this is called a conditional probability. So we need to calculate our denominator as well as our numerator for our probability. The given that at least one is working, I believe from above, if I remember, we calculated that in part A. Given that at least one is working. So we want the probability that 3 work, given that at least 1 works. And that such that or given conditional line there indicates that it's a conditional probability. Now, if I remember right, the answer to part A was, what's the probability at least 1 is working? And that would be 0.85. That is our new denominator. Ignoring the 0 case. 0 can't happen here, so at least 1 is working, 0.85. What's the probability that 3 are working? Probability of 3 working was 0.24. So this number right here, 0.24, has to be one of the numbers that made up the denominator. So what I mean is the denominator was 0.2 plus 0.4 plus 0.24. In a conditional probability, these are your only options now. So the numerator has to be one of these numbers, and it ends up being the 3 case. So calculating that, we would get 0.282 probability. 0.282. So those are the chances that 3 would work, given that at least 1 is working. So if you had the supporting work and the correct answer, that is also worth an E. So far, 3 out of 4 points. And then the last question is the trickiest of them all. Given that at least one ATM is working when the mall opens, would the expected value of the number of ATMs that are working be less than, equal to, or greater than the expected value from Part B? So in our table, when we calculated the expected value in Part B, we had all of these and we got a certain answer. So we multiplied the probability to its outcome and then added them all up. If we're saying that at least 1 is working, that means the 0 case isn't in play, and that probability, that 15% probability, is now going to kind of, in essence, make all of these probabilities to increase. So you can imagine if we don't have a 0 case anymore, all of these probabilities now, that's kind of like your complete total probability for the probability distribution. So imagine if this, just this 1, 2, 3, was your probability distribution. Each of the probabilities will have to be higher, and it's going to be more likely to find an ATM that's working. So in the earlier answer, we had 1.73 ATMs were working. If we get rid of the 0 case, it's going to be more likely to have an ATM working if it's like impossible for any of them to break. So the answer for Part D is that the probability, or the expected value, the expected number of ATMs working, would be bigger than that in Part B. Now, I wouldn't be surprised if students said that it would be the same, because you're thinking, well, when I calculated the expected value, 0 times this was just 0, so it didn't really affect it at all. But the problem with that thinking in Part D is that if this isn't an option at all, then these probabilities will now have to increase. And maybe some of you did this, that probability, these probabilities would actually increase to that same idea that we got in C. So you could actually calculate the new expected value. Oops, that's a 2. So the new denominator for each of these is 0.85. 0.21, 0.85. If you calculate each of these and add them together, you would get 1. That would be your new probability distribution. You weren't required to calculate the new expected value, but you could have. But to get an E on this question, on D, you would have to say that it is greater than the expected value and give some kind of rationale to justify your work. Now let me show you how they explained it in the scoring guide. Given that at least one ATM is working, the expected value of the number of working ATMs is greater, okay, by eliminating the possibility of 0 working ATMs. The probabilities for 1, 2, and 3 working ATMs all increase proportionally, so the expected value must also increase. Other ways of justifying that. There we go, right there. The top of the screen there. This is the recalculation of the new expected value. So you would get two machines that are working if you had calculated it that way. So definitely part D is the trickiest question to get full credit on. I never did something exactly like that, but we have worked with conditional probabilities, and we have worked with expected value before. Now let's look at the next question. Number 4. Number 4, you'll notice there is no part A, B, C, and D. This is your clue that there are 4 parts. This is do either an interval or a test, and notice just glancing at the question, I see an alpha level here, so we'll be doing a test. Also notice the language, is there convincing statistical evidence? That's also test language, not interval, but test. And also just noticing, it looks like I have a count of 26, a count of 15, and then a total sample size. Oh, and I have random assignment. These are all important things. It might help you on your test to circle the really important things. Also important that 1,000 volunteers, half of them were put into one group, half in the other group. So this tells me a lot of information. We have an experiment, so we have to be careful how we check our conditions with experiments. We also have count data, which is categorical data for proportions. So I'm going to use a prop test. And it looks like I have 2 groups. So at this point, it looks like I'm going to use a 2-prop Z test. 2-prop Z test at the 5% level. So what are the 4 steps? The 4 steps I need to include: I need to write hypotheses, number 1, state my hypotheses. Number 2, I need to check conditions, probably the most frequently missed part of it all. Number 3, I need to get a test statistic and a p-value with the 2-prop Z test. And then lastly, I need to conclude in context, and there are 3 elements that I must mention as I conclude in context. So we have a researcher conducted a medical study to investigate whether taking low-dose aspirin reduces, another important word, reduces the chance of developing colon cancer. As part of the study, 1,000 adult volunteers were randomly assigned to one of 2 groups. Half of them got the low-dose aspirin. The other half were in the control group that got a placebo. After 6 years, 15 of the people who took low-dose aspirin had developed colon cancer. 26 of the people who took the placebo had developed colon cancer. So notice there's more people developing colon cancer who were on the placebo. So we might have initial evidence, 15 is less than 26, we might have initial preliminary evidence that low-dose aspirin actually did help. At the significance level of 5%, do the data provide convincing evidence that low-dose aspirin each day helps reduce the chance of developing colon cancer? So the difference I observe is 15 out of 500 minus 26 out of 500. That is a difference, what is that, 9? No, 11. So that means 11 fewer individuals developed colon cancer when they were taking low-dose aspirin. There are 2 explanations for this difference that we observed. One is the chance explanation. One explanation is, well, the people were going to develop colon cancer either way at the same rate. Low-dose aspirin didn't really help, or it was just as effective as the placebo. Probably didn't do anything. That's the chance explanation. Just by random chance, we happen to, by the bad luck of the draw, put more people in the placebo group who were going to develop cancer anyway, regardless of the treatment. That's one explanation. The second explanation is, hey, maybe low-dose aspirin actually works. Maybe it actually helps reduce the chance of developing colon cancer. So, first, let's write our hypotheses. Our hypotheses, make sure you write the HO and the HA. That is required. And we have a difference in proportions. Now, I would kind of like to not have to get a negative. I kind of like positives better. But I guess either way, we can write it. So we have the proportion who are taking aspirin, ASP, minus the proportion who are taking the placebo. I'll just do PL for, well, maybe I'll just go placebo. Now that equals 0. Please be careful. Do not put hats on these proportions. We want to know about anyone taking low-dose aspirin similar to these volunteers. So that's an unknown parameter P. If you wrote P hat here, then you're just wrong. We already know the difference in P hats. That's negative 11 out of 500. We don't know the unknown actual difference in proportions. That's what we're doing a test to figure out if we have evidence to make a claim about it. The next one we have P asp minus P placebo. Now let's see, if we think aspirin's reducing the proportion, then I believe that would be a less than here, less than 0. If you did placebo minus the aspirin group, then it would be greater than 0. This would be accepted for full credit. You have identified your parameters. Now if you use like a P1 minus P2, you would have to define what P is. Well, really what P1 is and what P2 is. So it's much smarter to use these labels so it's clear what order you're subtracting. Now if we were to define our parameter, some students on the AP exam, probably, well, a lot of students I'm sure, said something like P is the proportion of patients who developed colon cancer with one of the two treatments. This would lose you points. I hope you realize why it would lose you points. Notice we used past tense. This is referring to the sample. We want to refer to the population of similar volunteers. So had this student said the proportion of patients who would develop colon cancer with or after taking aspirin or placebo, that would have been fine. But sadly, they did not. So if you had the hypotheses right, that would be an E. Looking at the next question, or the next part, we have, let's see, number 2, check conditions. So we're going to use a 2-prop Z test. The official name, be careful here because this confuses students. The official name is a 2-sample Z test for the difference in proportions. Difference in props. Got to give you props. Be really careful though because the calculator doesn't call it 2-sample Z test. If you use 2-sample Z test on your calculator, that will be wrong, so don't do that. So checking conditions. Do not put random check or random sample check. Those would be wrong. You would need to say we have random assignment. Of treatments. Right here. We were told that. If you said random sample, no, they were volunteers. Next, we need to check, is the sampling distribution roughly normal? Is the distribution is the distribution of the difference in p hats, p hat 1 minus p hat 2, is it roughly normal? Which it will be. The distribution of p hat 1 minus p hat 2 is roughly normal since the number of successes, which is the people who got cancer, is greater than or equal to 10. The number of failures, 500 minus that would be 485, greater than or equal to 10. This is really nice to write these out. This is going to help us with our calculator step. And then 26 is also greater than or equal to 10. And then 500 minus 26, 474, greater than or equal to 10. There you go. That's all we need to write. And then lastly, the independent condition is often not checked, often not required on the AP exam, so I'm not going to mention the independent condition. If you really wanted to, it would be wrong to mention the 10% because we didn't take a sample. The 10% condition is only when we sample from a population. We didn't do that. So if you mention the 10% condition, X that out and don't do that. The independent condition with experiments, we would just want to make sure that one person's developing of colon cancer is independent of another person's developing of colon cancer. So it's really based on the study design that we have. But either way, I'm not going to mention or write anything on my paper because it's more dangerous than it is beneficial to include the independent condition. Okay, so number 3 in our 4-step process, we have our hypotheses, we have the name of our test, 2-prop-z test, and we have our conditions checked. The conditions are met, so let's run our 2-prop-z test on our calculator. Running the test, 2-prop-z test, I got a z equals negative 1.83, and I got a p-value of 0.0335. Now, where did that come from? Here's the formula, probably the most dangerous formula to include, but kudos to you if you tried to include the formula. Our test statistic formula is our statistic, which was 15 over 500 minus 26 over 500, that was that negative 11 over 500, minus our null hypothesis, which is 0, over the square root, 500 here, 500 here. The numerator, however, is not 15 over 500 times 85 over 500. We would need to do the the combined p-hat, which would be the combined number of successes, 15 plus 26, over the combined sample size, which is 1,000. So we should actually have 41 over 1,000 times 959 over 1,000. And that's the same for both of these, 1,000, 1,000, 41, 959. That would give you the answer of negative 1.83. So be really careful. Again, kudos if you included that and did it correctly, but definitely could be a dangerous thing because many students would get a partial for not writing these numerators correctly. So the p-value is telling us, here's our standard curve now. We have 0 as the mean of a standard normal curve. We have 1 as the standard deviation, so negative 1.83 is going to be way over here. The p-value is this probability. Assuming there's no difference in the treatments, the probability that we would get a statistic like negative 11 over 500, or more surprising, just by random chance, is the p-value, 0.0335. So if you mention the name or the formula, but if you mention the name 2-prop-z test, which I had earlier, 2-prop-z test, and you included these and they're correct, that would be an E. Our last step in our 4-step process is to conclude in context. We're going to use our p-value, and we want to be really careful how we conclude. We can see if we can plagiarize well enough. So 0.3 was my p-value. So we would say since 0.0, what was it, 335, something like that, is less than our alpha level, it has crossed our threshold of surprise, so we will be surprised. These results don't often happen by chance. We would reject the null hypothesis, reject HO, and conclude that we have convincing evidence. These words are very helpful. You should include the words convincing evidence that taking low-dose aspirin each day would reduce, future or present or subjunctive, whatever it is, would reduce the chance of developing colon cancer among all people similar to the volunteers. Take the extra few seconds to write that out, and you will be very happy. So if you had the p-value and alpha level stated, if you mentioned what you're doing with the null hypothesis, and you mentioned that you have evidence for that up there with anything other than saying low-dose aspirin reduced, past tense, the chance of developing colon cancer. If you did those 3 things, then that would be an E. This question is a 4E question, so 4E's would be 4. If you had 3 E's and a partial, which is 3.5, halves are not given on the AP exam, so the reader would read your response and see if they should round up or down. And often in a case like this, they would round down to a 3. But how would they round up? They'd be looking for things like, did you state the hypotheses really well? Did you check the conditions really well? Did you, even best of all, did you include that formula with P hat C? Did you do that? Because that is, they even award you for things that they realize that's pretty tricky to get right. Those are the things they're looking for. And lastly, we have 3 multiple choice questions here for practice. First question is probability. Definitely want to talk about that. Suppose 3 students drop their phones and pick them up completely at random. What is the probability at least one student picks up the correct phone? So we want probability at least one is correct, smiley face, getting their phone. That's the same as the probability that 1, 2, or 3 get the correct phone. So I notice there's only one other case, and that would be 0. None of them get the correct phone. So if we did 1 minus the probability that 0 are happy, that should give us the probability that we're looking for. I just had an idea, actually, how it might be good to visualize this scenario. Let's just draw a picture. So here's person A, B, and C. Those are our people. What are the different scenarios? Well, they could all get their correct phone. A gets the A phone, B gets the B phone, C gets the C phone. Maybe A was correct, and the other 2 got mixed up. Those would be the wrong phone to the wrong people. Those are the only situations where A would get the correct phone. So now let's say B is found by A, and then this could be A or C. And if this is B, then that would be C or A. If this is C, that would be A and B. If this is C, that would be B and A. Those are the only cases. So our sample space has 6 possibilities. Which ones of these would be no one gets their phone right? Because we wanted probability that none, 1 minus the probability that none of them are correct. Well, this one has at least one that's correct. This one has at least one that is correct. This one has at least one that's correct. This one, none of them are correct. This one, none of them are correct. This one, at least one of them is correct. So if we did 1 minus 2 over 6, that would give us 4/6, or we could just count the check marks here, 1, 2, 3, 4. So the answer is 4/6. Four-sixths is the same as 2/3. So the probability that at least one gets the correct phone is 2/3. The next question. I should mention that number 1 is not binomial because you don't have independence. If one person gets the first phone, then it's impossible for another person to get that same phone. So you have to approach that in a different manner. Number 2, we have some hypotheses. This video is getting kind of long, so I hope you were able to get number 2. I will just briefly say, please do not pick D or E. They're off the table immediately. I don't even have to read. Don't choose those. Then I'm just looking for reading kind of quickly here. It sounds like it's just different. So my guess, and I could be wrong here because I didn't read it very thoroughly, my guess is that you would want the not equal to. Also notice in this computer output, you have the p-value given right here. The test statistic is 2. That's pretty far away, so it gives a rather low p-value. And then on the next question, I believe you're using that p-value to assess a claim. So just glancing at the answers, please do not pick accepting. Oh wait, what did that say? I don't really like accept language, but it is HA, so that might be okay. So at the 5% level, you should not be rejecting the null, so that answer would be wrong. This answer is looking pretty good. We cannot reject the null. You should not be accepting the alternative because the p-value is too high. So you can chat with your neighbor if you liked A or B, but at least my quick reading, E looked pretty good. But go ahead and chat about that. Thank you for watching this video. Good luck on the AP exam.